Okay, another Gauss's law problem. So we're going to have a line of charge density lambda. So we have constant charge density. Because this is an infinite line of charge, our total charge is infinity, but our charge per unit length, this is coulombs per meter, is this constant lambda. We want to find the electric field some distance away, some distance r away. Well, we're going to build a Gaussian surface that exploits the symmetry. So this line of charge has cylindrical symmetry, so on my Gaussian surface, will be a cylinder of radius r and length L. And that exploits the symmetry. Okay, now from symmetry, we know the electric field has to point away from the line. It has to. There's no way the electric field could point at, say, some angle like this. That wouldn't make any sense. If the line is straight up and down, why would the electric field point at some angle? That wouldn't make physical sense. We know it has to point directly away. So the electric field along our cylinder here has to point away on both sides. Also, the electric field has to be equal all along this side here. It wouldn't make any sense for the electric field to be higher here than it is here. This is an infinite line. This goes on forever, so if I stay the same distance away, the electric field has to be constant. So there we're exploiting the symmetry here. If we'd built a box instead of a cylinder, we wouldn't be able to say that. We wouldn't have something as pretty. Okay, then from this Gaussian surface, the double integral of E dot ds, the flux dA, ds, dA mean the same thing. The flux through this surface must be the charge enclosed over epsilon naught. Remember, we used divergence theorem to show that this is equal to the total flux. Integral of E dot dA, we've already said E points outward. dA is at every point on the sphere is a vector that points normal to, or the cylinder, a vector that points normal to the cylinder. These two vectors point in the same direction, so the dot product is just the magnitude. So that's magnitude E dA. And we said E must be constant along this entire boundary of the cylinder. Not on the top and bottom, but I'm not worried about that. In fact, we should point this out. Along these two surfaces here, since E points radially out away from the line, the flux through this, remember flux is E perpendicular through the surface. Here, E is parallel to the surface, so the flux through the top is 0, and the flux through the bottom is 0. So those top and bottom contribute nothing to this, the total flux through the surface. The flux will just be the integral of E dot dA through the outer side of the cylinder. Since E is constant along that, I can pull the E out and I get integral dA. And so I want, that's surface area, I want the surface area of the side of the cylinder without the top or bottom. If you remember, a cylinder can always be unwound, where here this is L, and the length of that rectangle, if we were to cut this cylinder and unwind it, the length of that would be the circumference, 2 pi r. So the flux through that surface will be magnitude of E 2 pi r. That should equal, now on this side, let's work on the other part of the problem. The charge enclosed. I have an infinite amount of charge total. I want to know how much lives inside this cylinder. Charge enclosed is always going to be your density times your appropriate units. That's charge per unit meter, so charge enclosed will be lambda charge per unit meter times our length, the number of meters. If I have a volume charge density, then charge enclosed will be density times volume enclosed. If I have an area charge density, charge per square meter, then charge enclosed will be density times area enclosed. Here it's density times length enclosed. So my charge enclosed is lambda L. Notice that I arbitrarily, when I built this Gaussian cylinder here, I arbitrarily made up the length. I called it L. No units from your Gaussian surface that you create that aren't relevant to the problem should end up in your final answer. There's no way there should be an L in the final answer. There should be an R, which is the radius here, because we know the electric field is going to depend on R. The further away we are, the less field we're going to have. So there should be an R in the answer, but there better not be an L. Okay, now we set these two equal. So the left-hand side was this, magnitude E 2 pi r equals the right side, don't forget the over epsilon naught, lambda L over epsilon naught. Oh, and I goofed here. Integral dA is length times width. I need an L here. So that was area. Length times width. Or if you want to call it length times width. Hey, look, the L cancels. I had to get magnitude of E. We know the direction already. It points radially out. Magnitude will be lambda over 2 pi r epsilon naught. And if you remember, we did this same problem by doing a finite section of wire, going through Coulomb's law, doing a really nasty integral. Then we took a limit as the length went to infinity, and we got exactly the same formula. This is the electric field from a line of charge. It drops off like 1 over r. So remember, for a point charge, we go like 1 over r squared. For an entire line of charge, we go like 1 over r. We'll see in another video, for an infinite sheet of charge, the electric field will be constant in all of space in magnitude.